Picture a nuclear-powered missile the size of a railroad locomotive screaming across the landscape at 3 times the speed of sound, spewing radioactive exhaust, and carrying 26 thermonuclear warheads with enough firepower to end civilization as we know it. This isn't science fiction, it's the terrifying reality of SLAM, a weapon so horrifying that even Cold War military planners eventually backed away from it. The most chilling part? Its nuclear reactor was actually ground-tested successfully, proving the technology worked. Today, as global tensions reach levels not seen since the 1960s and hypersonic weapons dominate headlines, we need to revisit this nightmare machine that nearly became operational. But to understand how such a monstrous weapon could even be conceived, we must first examine the desperate circumstances that drove its creation. The nuclear delivery crisis of the 1950s. By the mid-1950s, military planners on both sides of the Iron Curtain faced a stark reality that threatened to undermine the entire nuclear deterrent strategy. The atomic weapons they had spent billions developing were useless if they couldn't reliably reach their targets. The bomber aircraft tasked with carrying these weapons across the vast distances between hostile nations were becoming sitting ducks in an increasingly dangerous sky. The Boeing B-47 Stratojet required 10 to 12 hours to reach targets deep inside the Soviet Union, giving enemy defenses ample time to prepare. These aircraft faced the growing threat of sophisticated surface-to-air missile systems like the Soviet SA-2 guideline, which could engage targets at altitudes up to 25 kilometers. Both superpowers had deployed similar SAM systems by the mid-1950s, transforming what had once been a theoretical threat into a practical certainty that most bombers would never reach their destinations. Fighter interceptors posed an even more immediate danger. The Soviet MiG-19 and MiG-21 fighters could climb to bomber altitudes in minutes, while American F-101 Voodoos and F-102 Delta Daggers offered similar performance. These aircraft carried air-to-air missiles specifically designed to destroy large bombers. Intelligence estimates suggested that conventional bomber formations would suffer casualty rates exceeding 80% against prepared defenses. Military leaders recognized that speed alone might solve the penetration problem. The Convair B-58 Hustler achieved supersonic speeds, but carried a limited payload over short distances. The ambitious North American XB-70 Valkyrie program promised Mach 3 performance at extreme altitudes, but its enormous size and heat signature made it visible to radar systems hundreds of kilometers away. Even at 3 times the speed of sound, these aircraft still required hours to reach distant targets. The Soviets pursued similar approaches with the Myasishchev M50 Bounder and Tupolev Tu-22 Blinder programs. These aircraft incorporated advanced materials and propulsion systems, but faced the same fundamental limitations. High-speed flight consumed enormous amounts of fuel, reducing range and payload capacity. The faster these bombers flew, the more vulnerable they became to detection and interception. Range limitations created additional strategic vulnerabilities. Bombers needed forward bases to reach targets across intercontinental distances. These bases became obvious targets for preemptive strikes. The Strategic Air Command attempted to address this problem through continuous airborne alert missions, but even these operations left crews fatigued within 24 hours, underscoring the fundamental endurance limitations of conventional aircraft. The missile age promised to solve some of these problems, but created new ones. Early intercontinental ballistic missiles, like the Atlas, required hours of preparation before launch and used liquid fuels that couldn't be stored indefinitely. The missiles themselves were accurate enough to hit cities, but lacked the precision for military targets. This limitation forced planners to rely on enormous warheads that created unacceptable collateral damage. Submarine-launched ballistic missiles offered better survivability, but faced severe payload and range restrictions. The Polaris missile system under development could deliver warheads across 2,000 kilometers, but carried relatively small nuclear weapons. The submarines themselves moved slowly and required weeks to reach launch positions. These systems complemented rather than replaced the bomber force. By 1956, the strategic situation had reached a crisis point. traditional bombers were becoming obsolete faster than replacements could be developed, ballistic missiles remained years away from operational deployment in meaningful numbers. The gap between obsolete delivery systems and future capabilities threatened to leave both superpowers vulnerable to surprise attacks. This crisis of capability drove military planners to consider increasingly radical solutions. If conventional aircraft couldn't penetrate modern defenses, perhaps unconventional approaches might succeed. The concept of nuclear-powered flight had existed since the early 1950s, but had been dismissed as impractical due to shielding requirements. Manned aircraft needed heavy radiation shielding to protect crews, making them too heavy to carry meaningful payloads. The solution emerged from a simple but revolutionary insight. An unmanned nuclear-powered missile would eliminate the crew protection problem entirely. Without the need for biological shielding, designers could dedicate the entire aircraft to fuel, propulsion, and weapons. Nuclear propulsion offered virtually unlimited range and endurance, allowing missiles to remain airborne for days or weeks if necessary. This approach promised to solve multiple problems simultaneously. Nuclear-powered missiles could fly at low altitudes to avoid radar detection, eliminating the need for extreme speed. They could loiter over the ocean for extended periods before attacking, making them impossible to intercept during the boost phase. Most importantly, they could carry multiple warheads and attack numerous targets during a single mission. The concept gained momentum as engineers recognized that nuclear ramjet technology might actually be simpler than traditional reactor designs. Ramjets eliminated the need for complex turbine machinery, reducing the number of components that could fail under extreme conditions. The high-temperature operation actually improved reactor efficiency, making the entire system more practical than initially believed. As 1956 drew to a close, the United States Air Force made the fateful decision to pursue this nuclear-powered nightmare. The project would consume enormous resources and push the boundaries of materials science, nuclear engineering, and weapons design. What emerged from these strategic deliberations would challenge every assumption about the nature of warfare itself. Project Pluto's horrifying vision. The Air Force envisioned a weapon that would solve the bomber crisis through radical innovation. Project Pluto would create the Supersonic Low-Altitude Missile, an unmanned nuclear-powered cruise missile that combined the destructive power of an entire bomber squadron with the unstoppable persistence of a guided weapon. By removing the crew entirely, engineers could eliminate the massive radiation shielding that had doomed previous nuclear aircraft programs, dedicating the entire airframe to fuel, propulsion, and weapons. SLAM measured 27 meters in length and weighed 27.5 tons when fully loaded, making it roughly equivalent to 2 railroad locomotives placed end-to-end. The missile's nuclear ramjet engine would propel it at Mach 3 speeds while maintaining flight altitudes as low as 150 meters above the terrain. This combination of speed and altitude would allow the weapon to approach targets completely undetected by existing radar systems, which were optimized for high-altitude threats. The nuclear propulsion system promised capabilities that conventional missiles could never achieve. Where chemical rockets burned their fuel in minutes, the nuclear ramjet could operate continuously for several days. The Tory 2C reactor design consumed approximately 1% of its uranium fuel per day, allowing extended patrol missions that would keep enemy planners guessing about attack timing and targets. The reactor would generate over 500 megawatts of power while maintaining internal temperatures exceeding 2,500 degrees Fahrenheit. This tremendous heat would be channeled through the ramjet engine, creating thrust by superheating incoming air and expelling it at tremendous velocities. Mission profiles called for SLAM to launch from the continental United States and fly predetermined routes over the Pacific Ocean, circling in international waters until receiving attack orders. The missile could cover distances exceeding 182,000 kilometers without refueling, creating an airborne deterrent force that enemy nations could neither locate nor eliminate through preemptive strikes. Multiple SLAMs could patrol simultaneously, maintaining constant pressure on potential adversaries. The terrain following flight profile represented a revolutionary approach to penetrating enemy defenses. SLAM would navigate using an advanced system that compared onboard radar readings to stored topographical maps, allowing it to fly at consistent altitudes above ground level regardless of terrain variations. The missile would skim over mountains, follow river valleys, and weave between hills while maintaining its supersonic speed. This flight pattern would keep it below radar coverage until the final moments before impact. The payload capacity distinguished SLAM from every other weapon system conceived during the Cold War era. The missile could carry up to 26 separate thermonuclear warheads, each with a yield of 10 megatons. These weapons would be ejected vertically from the missile's fuselage as it overflew target areas, allowing a single SLAM to destroy dozens of cities during one mission. The total destructive potential represented more than 5,000 times the combined yield of the atomic bombs dropped on Hiroshima and Nagasaki. The weapon's secondary effects proved equally terrifying. SLAM would leave a trail of radioactive contamination along its entire flight path as the nuclear engine expelled fission products through its exhaust. The reactor operated without biological shielding, meaning that radioactive particles would stream from the missile throughout its mission. Communities beneath the flight path would receive radiation doses equivalent to standing near an unshielded nuclear reactor for extended periods. The superheated shock wave created by supersonic flight at such low altitudes would cause widespread destruction independent of the nuclear payload. The missile's passage would announce its presence through a continuous trail of devastation even before reaching its primary targets, as the intense heat and pressure waves scorched everything in its path. Military planners recognized that SLAM represented a new category of psychological warfare. The weapon's ability to loiter over enemy territory for extended periods would create unprecedented terror among hostile populations. Unlike ballistic missiles that provided only minutes of warning, SLAM could circle overhead for days, creating sustained panic and forcing enemy leaders to evacuate population centers repeatedly. The mere knowledge that such weapons existed would fundamentally alter the strategic calculations of potential adversaries. The technical challenges required to make this nightmare operational pushed the boundaries of existing science and engineering. The nuclear reactor had to operate reliably at temperatures that would melt conventional materials while withstanding the extreme vibrations and stresses of supersonic flight. The ramjet engine needed to function continuously for days without maintenance while processing enormous volumes of air contaminated with radioactive particles. The guidance system required innovations in terrain-following navigation that wouldn't become standard in military aircraft for another 2 decades. SLAM needed to process radar data in real time, compare it to stored maps, and make navigation adjustments while traveling at 3 times the speed of sound. The electronic components had to function reliably in the intense radiation environment created by the nuclear reactor. Perhaps most challenging was the warhead deployment system. The missile needed to accurately deliver nuclear weapons to multiple targets while maintaining its own flight path. Each warhead required its own guidance system and parachute deployment mechanism, adding complexity and weight to an already demanding design. Despite these formidable obstacles, the project received official approval and substantial funding in 1957. The Air Force committed to a multi-year development program that would employ thousands of scientists and engineers. The Lawrence Livermore National Laboratory assumed responsibility for reactor development, bringing together some of the most accomplished nuclear engineers in the United States. These experts would soon discover that turning Project Pluto's vision into reality would require solving problems that seemed to violate the fundamental laws of physics and material science. The impossible engineering challenge. Dr. Theodore Merkel and his team at Lawrence Livermore National Laboratory confronted 10 major research and development areas that had to be solved simultaneously to produce a working nuclear ramjet engine. Previous attempts at nuclear-powered aircraft had failed spectacularly, not because the reactors wouldn't work, but because the shielding needed to protect human crews weighed as much as the intended bomb loads. the aircraft nuclear propulsion program had spent over $1 billion trying to solve this fundamental problem, producing aircraft that were too heavy to carry meaningful payloads. SLAM eliminated the crew protection problem entirely by removing humans from the equation. Without pilots or navigators aboard, engineers could eliminate the massive lead and concrete shielding that had doomed earlier projects. This breakthrough freed up thousands of pounds of weight capacity for fuel, weapons, and propulsion systems. However, removing the crew created entirely new challenges that pushed the boundaries of materials science and nuclear engineering into uncharted territory. The operating environment inside a nuclear ramjet exceeded anything previously attempted in reactor design. The engine would generate internal temperatures reaching 2,000 degrees Celsius, hot enough to melt steel and most conventional aerospace materials. These extreme temperatures were necessary to heat incoming air to the velocities required for ramjet propulsion. Intense radiation fields created additional material stresses that conventional engineering couldn't address. The reactor would produce both neutron and gamma radiation at levels far exceeding those found in stationary power reactors, gradually altering the atomic structure of surrounding materials and causing them to become brittle without warning. The supersonic airflow through the ramjet created mechanical stresses that compounded the thermal and radiation challenges. Air entering the engine inlet would be compressed and heated to temperatures exceeding 1,000 degrees Celsius before reaching the reactor core. This superheated air would flow through the reactor at velocities approaching 300 meters per second, creating tremendous pressure, differentials, and vibration loads throughout the engine structure. These extreme conditions exceeded the operational limits of every known material. Steel would melt at the required operating temperatures. Aluminum would vaporize almost instantly. Even exotic aerospace alloys like Inconel and Hastelloy would fail within hours under such conditions. The project required materials that could maintain structural integrity while simultaneously resisting thermal shock, radiation damage, and mechanical stress. The solution emerged from a fundamental redesign of the propulsion concept itself. Rather than adapting existing turbojet technology, Merkel's team chose to develop a nuclear ramjet engine that eliminated most moving parts. Traditional turbojet engines relied on complex compressor and turbine assemblies with thousands of precisely machined components. These mechanical systems would fail immediately under the extreme conditions required for nuclear propulsion. Ramjets offered a simpler approach that matched the unique requirements of nuclear power, containing no compressors, turbines, or other rotating machinery. Instead, they relied on the forward motion of the aircraft to compress incoming air through carefully shaped inlet ducts. The reactor core breakthrough required 465,000 hexagonal fuel elements made from beryllium oxide mixed with uranium oxide enriched to 93.2% uranium-235. Engineers added zirconia and yttria for stability, creating a ceramic fuel mixture that could withstand the extreme operating environment. The beryllium oxide served as a neutron moderator capable of surviving temperatures exceeding 2,000 degrees Celsius, according to Livermore reports. Each fuel element measured 7.5 millimeters across its hexagonal cross-section with a 7.5 millimeter diameter hole through its center, designed to pack closely together in a honeycomb pattern while allowing adequate airflow. The core's porcelain company, better known for producing beer bottles and ceramic fermentation equipment, became the unlikely partner responsible for manufacturing these fuel elements. The production process involved mixing sinterable beryllium oxide powder with oralloy uranyl nitrate, yttrium nitrate, and zirconium nitrate to form a slurry. This mixture had to be carefully controlled to prevent accidental criticality during manufacturing, requiring specialized machinery that could detect dangerous neutron flux levels and immediately halt production if criticality appeared imminent. The fuel elements were supported by a framework of metal tie rods made from Rene 41 and Hastelloy R235 alloys, designed to operate at temperatures up to 760 degrees Celsius while maintaining sufficient strength to hold the reactor core together under extreme aerodynamic loads. Ceramic guard tubes surrounded the tie rods to provide additional structural support and thermal insulation. SLAM's airframe design reflected the radical nature of its propulsion system. The missile resembled a wingless flying crowbar with a rectangular cross-section optimized for housing the nuclear reactor and payload bay. The design eliminated traditional aircraft features like wings and vertical stabilizers, relying instead on small control surfaces and the inherent stability of its high-speed flight profile. The streamlined fuselage measured 27 meters in length and incorporated air intakes at the front to feed the ramjet engine, with the reactor positioned amidships and the payload bay extending toward the rear. By 1960, 3 years after the project's inception, the first prototype reactor was ready for testing. The combination of innovative materials, radical design concepts, and manufacturing breakthroughs had transformed an impossible engineering challenge into a working nuclear engine. However, testing this revolutionary propulsion system would require constructing the most elaborate and dangerous experimental facility ever built. Jackass Flats, building a nuclear test site.